Okay, so that's just so that if you need to come back to anything, like I say, I'll send these out fairly quickly after the webinar, hopefully by the end of the day certainly, and also if anybody else joins or you want to show it to others, then feel free. Okay, so what I'm going to do to start off with is basically have a quick brief over guide of Qtegra. I'm sure you've all sort of heard some of it before, but I think if we go through it, then we can make sure we're all at the same level. So hopefully, and I'm sure somebody will send me a question if they can't see it in a moment, you should be able to see my screen with Qtegra on it. So on the first part, we have what we call the dashboard, which is, if you like, the sort of main control interface for the instrument itself. Now, actually, I'm in a meeting room, so I don't have an actual instrument here to show you. And so as you can see, all the interlock lights for the ICP are actually all greyed out. There's no connection. Of course, once you've connected your instrument, as you see on yours, then they go green if they're fine, and if there's a failure for some reason, then of course red shows, and that will stop the instrument for a safety feature. In this particular case, I've set it up as a 7600 duo, so we've got all of the features to look at. But of course, if you've got a 74 or a 72, then only the appropriate features are shown on your dashboard. So we can do several features from here that I'll have to just talk through really, because like I said, I don't have an instrument. With the Get Ready feature, which is here, of course, if we press this will light the plasma, and it will bring up a little window to allow us several settings, such as to put an automatic plasma stabilization or warm-up time. We can do a spectral optimization, which I do suggest, and it only takes about a minute. Basically, that uses two carbon lines from the carbon dioxide in the air of the plasma to just make sure that the detector is looking in the right place, essentially, that all the wavelengths line up with where they should be, and if not, then adjusts appropriately. And finally, there's a lot of performance checks we can put in there as well, which use the test solution, the multi-element test solution that comes with the ICP. And this can just be used to check the performance of the instrument in advance of an analysis, so some detection limits or sensitivity tests or RSD tests. Once we've got the plasma alight, we can do a torch alignment, which is here, which will just make sure that the actual view is looking in the right position down the viewing channel, down the plasma. And if you remove the torch and replace it, then you should perform a torch alignment. We have the option for a spectral optimization. Excuse me, I have a bit of a cold. So we can run one of those manually ourselves as well. And we can adjust all of the plasma settings, the gas flows and the RF power, and the pump speeds here manually adjusting on our instrument. Finally, it also shows we have, in this case, I've set it up with a CTAC ASX 520 auto sampler, and it's set on fake mode, so it thinks it's connected. If we press this button here, then we can see the setup for the auto sampler. And if we had a real auto sampler, once we've changed all the files and set it up as we like, then we can actually click on any of the sample positions and the auto sampler will move to that position. You might want to set it to rinse, for example, or to just go for a manual sample on a single position. Okay. Excuse me, sorry. Okay, so basically that's controlling our instrument, and that's the sort of brief overview of that. I'll very just quickly ask if anyone does have any questions on this. It's quite simple, so I imagine not. If you want to ask a question, then please press *6 to unmute your line. Okay, well, I'll leave that as no question, so we'll just move on to the next part. So as we can see down the side, we have several sections here from the dashboard. The next one is the LabBooks. Now, the system of LabBooks in Qtegra is designed so that our LabBook is like a physical LabBook that you would have in your lab. So it contains all of your samples, your plasma settings, your method parameters, as well as all of the results and the reports and everything. So the entire system entire experiment is collected in this single lab book. So these are what we do for our experiments. So hopefully you've had an email around that contains a lab book that I've sent around that I will be referencing a little bit later, called Demonstration. So basically with the first page of LabBook, there's a few ways we can go around creating one. So we would first start with our name, so I'll call it Demonstration 1. We can decide a location, so if we want to start making some folders, for example, for easy organisation, that's easy to do. And then there are 3 ways to create a LabBook, so I'm actually going to start at the bottom. So our first one would be to create a LabBook from a blank template, which is obviously start one from scratch. And the evaluation mode has 2 modes at the moment, eQuant, which is what we call an external quantification, or like a standard calibration solutions. Or we can just use raw data, so if we're just interested in the raw data, the intensities, then we can use that at the moment. And there will be more coming for the ICP OES, and as you will see if you go on the call next week with Julian, there are several more already available for the ICAT-Q ICP MS. The second option we've got is to create a new LabBook from an existing LabBook. So if we've already got one that we've used, such as the demonstration I've already sent you, I could create a replica version of this with none of the samples analysed. And that will copy all of the information, all of the meta parameters and the sample list and everything along into the new LabBook, where we can alter it if we want to if necessary and simply run it again. So if you're running the same samples with the same method every day, then that's quite a good way to do that. And finally we have the third one, which is to create a LabBook from an existing template. So we have, as we can see, another option here below the LabBooks, which is called templates, which we'll look at in a moment. Then we can create basically a template for a LabBook. So we can set in there all the method parameters, the instrument settings, and basically our QC protocols. So your calibrations to run at the beginning, QCs to run at the beginning, any QC samples every 20 samples, for example, and things at the end as well. So we would then, perhaps, if you have a routine method that you need to run for unknown samples each day, then you could set a template up with your QC protocols and create a LabBook each day from this. And all you simply do would be to tick the name of the template, in which case you don't have one. I'll set one up later. And you'd write in the number of samples and press create, and it would simply fill in all the samples into the template and create a LabBook from it. As we can also see, there's a tick box here, and you can, if you have a LIMS system, you can get your LIMS to create a CSV file that lists all of your sample names and such. And then we can actually, set up our LabBook using this list from the CSV file. So this will label all the samples, put the positions in, and carry every piece of information from your LIMS into the LabBook. So what I'm going to do to start with is basically go through creating a LabBook from scratch. So if we select the correct one and press create LabBook, what we can see is obviously we start with our periodic table. On the left hand side we have a series of steps that we will move through to set up our LabBook. And what I'm going to do to begin with is just going to be a simple one, and then some of the extra features that we'll talk through, I'll come through and add those on a bit at a time, so that you can ask questions and we can try and keep it an easy learning experience. So obviously, like I say, the first page is analytes, and this is our periodic table, which I'm sure you're all familiar with. And simply we can select an element by pressing left-clicking, for example on magnesium, and this will add magnesium line, and it will add the default magnesium line. If you want to look at other magnesium lines or select multiple ones, we can press actually right-click on the magnesium, and we get this window instead. So we actually have a selection of magnesium lines here in order of relative intensity, so that the stronger lines for best sensitivity at the top, and the weaker lines for higher concentrations, for example, at the bottom. And a nice graph that would show us any potential interferences as well, and how they're relative to the magnesium line we're interested in. So it's already ticked the top one, which was our default one from when I left clicked it. But if we want to select some other lines, we could also go and select several others. Okay, so we can see with this one, then it says the red is actually an interference, although in this case it happens to be another magnesium line. So we can see from some of the potential interferences and how they show up. So that's quite a nice tool for looking at that. So I'll just set up a couple of elements to start with. So I'll just keep that as a basic lab book for the moment, and then we can set up some of the features. And then when I bring up this other lab book I've sent you, the demonstration, we can see results and talk through it. It's a bit more of a complicated lab book. So once we've chosen all of our wavelengths, and remember at this point, if you want to use an internal standard, then you need to add it in here as well, which we'll come back to. The next line is the measure modes. And in here we set basically our plasma parameters and our viewing parameters as well. That's how we can look at the plasma and get our data out. So to start with, because we have a duo instrument, we have the two modes here, the axial and radial modes. If you have a radial only instrument, of course only radial is there. And what we can do is we can change the settings separately for the ultraviolet and the visible lines. So basically the reason we have these two sections is the way the ICAP actually works, is it actually views all of the UV lines first, does all the readings for the ultraviolet lines, so that's from 167 to 230 nanometers. Once those are read, it will then move over and read the visible lines, which is actually 200 all the way up to 847 at the top nanometers, and read those separately. Now, the reason for this is it does actually provide much better data because you can get much better focus on the specific lines you're looking at, so it increases your sensitivity and your stability significantly. But it is worth remembering, of course, that this actually slightly increases the analysis time and is worth considering when you have internal standards as well. So typically, the default settings are 15 seconds for your ultraviolet lines and 5 seconds for your visible lines. Of course, you can change these if you like. For example, you might only say 10. You can change your plasma power settings. So if you've got heavy matrix samples, you might want more power. Your nebulizer gas flow can be altered as well. 0.5 is a good default, but it depends on the nebulizer settings, the spray chamber you've got, and the type of samples you're analysing as well. Then you might want to vary this. And a good guide is for a radial instrument 0.45, and for a duo 0.55 is sort of suggested as a good standard. What we can do here at the bottom, the next bit is we can do what we call a capture full frame. And we'll talk through it a bit more later, and I'll come back to it. But as we can see the settings there, we can decide for each 4 of the modes, the radial UV, the radial visible, the actual UV, and the actual visual. Then we can decide if we want to do a full frame. We can either say yes, or we can use what we call the IntelliFrame. So if we say yes, again, we can set our exposure time. So we might want that to be the same as our analysis. Or if we use the IntelliFrame, it actually intelligently detects the exposure time for each of the wavelengths on there. So for the moment I'll say no. Like I say, I'll come back and have a look at it a bit later. We also have our 3 other gases. So we have our coolant gas, which is sort of also called the primary gas on some instruments, and the plasma gas. And this is kind of the main gas in the plasma. So this provides the majority of the argon that actually lights the plasma itself and provides the plasma. But it also helps keep the plasma away from the tubes in the torch to protect them, as well as shaping the plasma. So it's particularly important that it's stable over for actual viewing. We have the auxiliary gas, which is from the tube between the intermediary and the centre tube, and this one holds the position of the plasma. So as you can see, it's much less, it's only half a litre a minute, and this actually positions where the plasma is in the torch. So this one's much more important for radial views, so that you're making sure that you're looking in the right place on the plasma. And then finally, if you've got a 7600 or bought an additional gas accessory for a different model, then we can add an additional gas, which is used for organics analysis and solvents and such. And basically, you would add air into the system, into your auxiliary gas, and the oxygen from the air will burn with the carbon soot created from your solvent and turn it to carbon dioxide, and basically keeps your torch much cleaner for much longer. Okay, so I'll waffle the lid. So basically, as we see, we can easily swap and create our own different separate settings for each 4 of the viewing modes. The next section, once we've set all this, is what we call the acquisition parameters. So this is how the actual instrument will read the data that comes up for each wavelength. So we have 3 settings here. For a 7600, that's 3, the normal, the speed, and the sprint mode. If you have a 7400, it has normal and speed mode, and the 7200 just has normal mode. Okay, so the basic differences, I'll quickly outline each of them. With normal mode, which all instruments have, if I move back to this we can see a bit easier. Basically it will run for example, the radial UV repeat number 1, radial visible repeat number 1, actual visible repeat number 1, and actual UV repeat number 1, then return to radial UV repeat number 2, radial visible repeat number 2, etc., etc. So essentially it will read the first repeat for each of the analysis types, and then the second repeat for each analysis types, and then the third repeat, and so on if you've got more. If you use the speed mode here, it will basically go to radial UV and do 3 repeats. It will go to radial visible, do 3 repeats, actual UV, 3 repeats, actual visible, 3 repeats. So there's much less moving for each of the mirrors, and basically to change the plasma views. And so it actually saves about 30% of the analysis time per sample, because it essentially only has 3 mirror movements to do instead of 9, or possibly more than that. And sprint mode is a special kind of mode. So if you're doing what we call, what's going on here? Basically, if you want to check the rough levels of instruments and basically track how concentrations are changing over time, and rather than getting a specific concentration reading. So for example, for targeted fertilization samples, or if you're doing lubrication oil analysis and you're simply interested in how the levels are going up and down, and not very high accuracy concentration, then we can use sprint mode. So what this does is a different algorithm for reading the chip. So instead of doing a pre-test and making sure it's measuring all the different wavelengths and reading them at the correct time off the chip, it just assumes they're all correct and goes in and reads them all for the set amount of time. So the advantage of this is it's much quicker. Again, it saves some significant time on the analysis. Unfortunately, it doesn't. It means that the chip isn't being utilised correctly for all its saturation and its anti-blooming effects. And so you've got to be very careful which wavelengths you pick, because they can very easily saturate with different types of samples. So, like I say, it's good for just checking levels on samples and seeing when they go down or up, rather than getting accurate measurements. Okay, so once we've selected our mode, and typically probably speed mode, we can adjust our pump speed, so it might be 50 RPM. We can have what we call our flush pump speed, which we might set to 100. And this basically makes that the pump goes faster as your sample's being taken in during the uptake or flush time. and then we'll slow down for the analysis to the pump speed, and then actually when the rinse occurs, it will speed back up to the flush pump speed. And the final little setting is the pump stabilization time. So that's basically a delay time set into the instrument to make sure that the pump has stabilized between changing. Excuse me. For example, if we do have these settings, for example 50 to 100, I would suggest at least a 1 second stabilization time. And it would just make sure that once the pump is changed back to 50 RPM, for example, it will wait for a single second to make sure that the pump is stable. There's an option on the right for laser triggering, but I won't discuss it in this webinar. And also we can see some of the other sections. So we've got all of our wavelengths we've selected. It tells us which of what we call the slit positions, so the low being the UV and the high being the visible, as discussed earlier. We can decide whether we want to view them with an actual view or a radial view. So we can select 2, for example, and we can choose the width. So it's basically the amount of pixels that our subarray will look across and detect them. So we can change them up to 24 is our maximum. So it gives you the maximum width for subarray to check your backgrounds and find the most stable background. But it does take slightly more time for the analysis because there's more pixels to check and read. So 12 or 13 is a good default, but if you are struggling to get find a stable background position, then I suggest you try widening the subarray. And the only other bits that worth just pointing out are the left blanks, so we can decide whether they're fixed or auto or none. So if we know that there's an interference on one of the sides of the peak, then we can switch it off. We'll set the auto detect position. Okay, so once we've set up our acquisition parameters and our measure modes, so essentially how will the plasma maintain itself, which is the measure modes, and how will it take its data, we have some other features. So we have an intelligent uptake and rinse, which again I'll come back to and have a quick talk through later. We have our standards, so we can create our calibration standards and our QC standards here. Again, I'll come back in 2 seconds for this one. And we have one called quantification. So the difference between the measure modes and the acquisition parameters and the quantification, essentially the first two, the measure modes, the acquisition parameters, are sort of physical settings. What settings do we put the plasma to? And then how do we physically read the data? And then the quantification is what do we do with the data after we've acquired it? How do we quantify it, essentially? So as you can see, again, we've got all of our wavelengths. It tells us what our measure modes are. We can decide whether we want to quantify it or not, so we can easily just turn one off if we don't want it, but don't want to remove it completely. We can set up internal standards, and that will come back as one of the separate topics I'll talk about. We can set what we call a standard range and a switch point, so this is a part of a feature called line switching, which again I should come back and talk to. It's quite a powerful feature. And we can set our fit type, so it could be linear or second order. We can choose to weight our calibration, or we can decide where to force the calibration through. So it could be blank, 0, or kind of no forcing. Excuse me. Just slowly dying here. The other thing worth pointing out on this page, of course, is our use quality control feature. So if we tick this, we can see an extra little function is added at the bottom called quality control. Quickly look at that, and we can set our quality control settings basically for that, or the pass-fail criteria. So again, I'll come on and talk to that one in a moment. So that's our quantification page, and like I say, some of it, line switching and the internal standard I'll come back to in a moment. So we have our standards. So if we go back to our standards, we would need to set up our calibration standards and our QC standards on this page. There's a few features. So if we press new, we can choose what type of standard we want to create. So we could have an elemental standard, which would be a standard if you like, a normal one. And we could call this a calibration standard. If we want, we can add a description. We could call that cal stock. And then there's an option for create the standard from the analyte list. So if we press this, it will add the 2 elements that we've got in our element list as default. If you don't press it, then it's blank and you have to add them yourself. We can add more or take some away if we wish from this list as well. So for example, if I say there's Chrome in there as well. Now, it seems a bit daft doing that, but there is a reason for it. So for the moment, I will add that in, and we can see why. So we might have a calibration stock solution that's 10 ppm. We've created. So there's actually a feature. If we right-click, we can say what we call path to global. And this will actually create this standard in a global library of standards in Qtegra. So if we were to create a new lab book, and so we want to use this standard here as well, by pressing on open, we can actually see the one I've created here, the calibration standard, which is the same one I've created. But of course we've already got that one on, so I can't open it up. So that's why you might want to add different elements that aren't in this particular analysis, because they're in your standard and you might want them for a different analysis. Okay, so we'll just remove it for the moment. So there are 2 ways we can go about creating a calibration graph. In this particular instance, we could use this one calibration stock solution, perform manual dilutions, and then basically tell the instrument which manual dilutions we've performed. So we might do a times 10 dilution and a times 100 dilution, which would obviously give us 1 ppm and 0.1 ppm. And we could then create a calibration from those 3 positions. Alternatively, we could easily create them all manually from here. So we might call it cal standard 1, which could be 10 ppm. We could make one called cal standard 2. We could change this to 1 ppm, for example, and cal standard 3. Make that 0. So that's a kind of 2 ways to go around it, and I will set them both up to show you how easy it is to set up either way. The other thing that we need to remember, if we want to use quality control standards, we need to create them here as well. So we might have one that we call QC standards. Again, we're going to create it in the same height, and perhaps we'll call that, make that 5 ppm. Okay. So that basically is the main part of setting up the lab book, the method itself, if you like. So I'm going to stop and ask if anyone's got any questions at this point. So if you want to use the phone, *6 will unmute you, or perhaps type them into the questions on the bottom. So I've got one. On what basis we need to change the exposure time? Okay, that's a pretty good question. Okay, so if we just quickly go back. So basically the exposure time is the amount of time that the light falls on the detector, so it analyzes it. So for each of these viewing modes, then we obviously set it so that this particular set of light falls on the detector in its 2D sort of image. And we basically read each of the lines in that group for the amount of time we've set as our exposure time. So in this particular case, the radial UV would read for 10 seconds and then the visible for 5 seconds. Now, there's always a balancing act here. Now, the reason you'd increase this, for example, is if you want better detection limits, better sensitivity. Because as we let the light fall on the detector longer, then we can get higher counts, more stable counts, so we will get better sensitivity, and so a better detection limits ultimately. And now the opposite being, of course, as you increase this time, then that increases our analysis time. The longer you have to leave the light to fall on the detector, then of course the longer the analysis time takes. And remember, typically for each of these there's 3 repeats, so changing it from 10 to 15 seconds will actually add 5 seconds per repeat, so that's 15. So you can actually decrease them to improve your speed of analysis. So you've got to remember that with this, it's always a balancing act between the speed of analysis and the sensitivity of the instrument. And so the typical ones of 15 and 5 seconds are good starting points. Like if you say, like, for example, if you find you need better detection limits, then of course increase them. The other question is standards in reverse order. Well, you can build your standards however you like. I've just happened to have built them in reverse order. Typically, I would do them the other way around, but yeah, I just happen to have created them that way around because I was thinking about what to say next. So there's no particular reason that you have to build them in any direction you like, or in any. It doesn't even have to be in a direction. You could just build them, analyze them at random. So as you see, when we build the sample list, then I can change that around as well. Okay, so I take it there are no more questions. Oh, I've got some more from. Okay. Is it possible to open these features without an instrument connected? I think you mean the get ready features. You can't open them without connecting an instrument as such. Unfortunately, I've got a software simulator that seems to not be working at the moment, so I was planning to use that to show you, and I can't get it to work. So unfortunately, I can't show you the get ready features such without an instrument. But there is a series of videos that I've created that are actually available on YouTube or can be sent to you, which go through explaining quite a lot of these features as small how-to guides, and one of them is the get ready features. So when I send out the recording of this, then I will add a link to this YouTube channel. And like so it says, can the default values on the nebulizer gas be changed somewhere? Actually, at the moment, no, they can't. It just has a default settings that are on each of the acquisition modes, unfortunately. And so if we're going to change them, then yeah, you'll unfortunately have to change them yourself. But if you do need help deciding what's the best nebulizer gas, then we can help with that. Or you can do some tests as well that are quite a good idea to check it. Basically, you'd set up a small lab book with the elements that you're interested in, and run a series of different nebulizer gas flows to the same sample so you can see which gives the best results. The thing that needs remembering as well is that that is also a slightly balancing game, really, because higher nebulizer gas will actually put more sample in your plasma. So in theory it should give you better sensitivity, and for some elements it certainly does. Certainly the lower wavelength elements, it provides better sensitivity. The problem is you get the higher wavelengths, potassium and sodium, for example, you may well have noticed, have very high backgrounds. So as you actually put more sample into the plasma, your backgrounds increase more than the peaks. So it degrades your sensitivity in that sense, because your signal to background ratio is poorer. So again, it's a slightly balancing act between some elements and the others. Okay, let's check there's no more. Right, okay, one more saying the QC standard is needed. If you wish to use QC samples, then you need to create a QC standard, which is basically where you set the concentration of the QC sample that you're going to be analysing. You could set 2 or 3 or more. Again, we can do it in a similar way of setting the dilutions that we perform manually, or setting them as all separate standards. That's essentially where we set the concentration for our QC samples, and then the pass-fail limits are in a slightly different section. Okay, so if that's all of the questions, yeah, I think so. Okay, so we'll move on. So I'll quickly describe this quality control we have then. So as we can see, we have a QC standard in our standards, so we're going to use QC, and we've ticked the use quality control feature in quantification. So this allows us to set up this quality control. And basically, as we can see here, is a list of all different QC tests. And these are all taken from the US EPA 200.7 analysis method. And mostly a fairly standard, but I will go through some of them. It's worth noting that we can actually create our own one. So if we want to create one that isn't on our list, we can do that as well. But basically the idea being is we have a few different blank tests. So what we call our initial calibration blank or a continuing calibration blank. We can have a memory test blank, which we basically check if we have any memory effects or carryover. Perhaps a preparation blank as well, that might be from our sample digest or preparation technique. Now as you can see, what we have on the side is a warning and fail limit for here for each element. Okay, so if I just move to our initial calibration blank, basically what we can do is we can set separate warning and fail limits for each of these different types of standards. Now, basically what these are is there's a little one at the top here called Edit the Contract Required Detection Limits. There's a little gear there. If we open this up, in here we would set what's our sort of detection limits or our required detection limits for this analysis. So it could be 1 ppm, obviously it's quite a low detection limit, but it's default like that for a reason. And then the warning and failure limits are compared against these detections. So our warning limit would be basically 1 or 100% of this concentration we've set here, and the failure limit is 200% of the limit here. So in this case, the warning limit is 1 ppm and the failure limit is 2 ppm. So the reason I've had these set as 1 ppm as our defaults, you can actually just go in here and set the changes here, and it will apply them as if these were the actual limits in ppm, your warning and failure limits. Alternatively, you can change them as percentages and set your correct required detection limits. So for example, if I want my detection limits sort of as pass-fails for my blanks, I might set it as 0.1. I might set these as 0.1 for them all. We can right select and go down here. And then in this case, it will be a warning limit if it's over 0.1 ppm, and a failure limit at 0.2. And I might wish to change this down here. I'll put 1 here. Go down. So in this particular case, because we have our required detection limit at 0.1, if they're over 0.05, there will be a warning limit, and if they're over 0.1, then it will be a failure limit. Like I say, if you leave them all at 1 ppm in the detection limits, then you can apply the actual, for example, if I leave them all as 1, which is their default, in this case 0.5 ppm will be a warning limit, and 1 ppm will be a failure limit. And we can actually apply them separately for each of the different tests. So our initial one, for example, like I say, the US EPA, you require tighter limits for your initial calibration blank than for your continuing calibration blank. The next section is the calibration tests. And basically these are QC samples, so you would set them using the QC standard that we've created before. And you can set basically pass and failure and warning limits in here. So in this case it's a warning if it's beyond more than 20% either way, and then if it's more than 25 then it becomes a failure limit. And again we can change these for all the different samples that we have: initial calibration, verifications, the continuing ones, and quality control standards. We can set a series of duplicates as well, so we can run two samples that are the same sample and make sure we're getting the same readings back. And again, our pass and fail limits, and a series of serial dilutions as well. So you can run the same, dilute the sample with a few different dilution ratios, and run to compare to make sure they're all coming back the same. We have some spike tests, so we can spike a blank or a sample or a post-digestion spike. I'm not going to go into very much detail with these. As I say, there will be videos that you can look at if you're interested. We can set a regression coefficient verification, so this is essentially our warning and fail limits for our R-squared value on our calibration. And some relative stability data as well, so if our samples are greater than 5% RSDs as well, then it can flag up and warn us about that too. And finally, our internal standard test, so we can set our limits if we're using an internal standard, what are the pass and failure limits for the recoveries on the internal standard. Just quickly go back to here, the section we can have for the test details. Again, can be varied for each of these different sample types, but we can set how many different analytes it takes to make a failure. One is usually the default. How many warnings does it take to make a failure as well? Well, again, we can set that. And we can decide what to do if it fails. So in this case, if the QC fails, we might say rinse and repeat the sample. If it fails again, then we might wish to recalibrate and reacquire all the data. And then if it continues to fail, we might say abort the experiment. And again, you can set how many times to do each of these actions before it moves on to the next one. Okay, so that's setting up the method really. Check there are no questions. What does it mean for the failure and warning limits? Okay, that's basically a sort of standard QC system. So if your QC would fall, in this case, outside 80% or 120% of the sample's concentration, the standard's concentration, then we class that as what we call a warning limit. So we say that it started to deviate from where it should be. And then if it goes the further past the 25% either way, then we call that failure. So basically a failure, we would say it's deviated too much from where it should be. The quality control standard has failed, and what we need to do is find out why it's failed and rerun that particular standard and any associated samples that are associated with it as well, and reanalyze and perhaps even reprepare if we found that there's a contamination or a standard production issue. What we have a warning limit as, typically they're designed so that if you have one warning limit on its own, you can say, well, you're aware that it is deviated, but it's not, and not so much as we're going to fail everything. But you're aware it's close to the line. So if we have two warning limits, usually consecutively is usually the system, then we can count those as a failure. We can say, well, they've deviated by just, not enough to fail it, but consistently deviated by that amount. And we can say, well, the whole system is obviously not quite right. We would fail it, and again, try and discover what the reason is, and have to reanalyze the QCs and the associated samples. So the system I've set up here at the top is quite a good way of discovering what's going on. So we might run it. It might do a failure or a warning. It would clean the whole system and try running it again. It could have been a contamination or something very simple that's caused it to go off once. Again, of course, if that still fails, then we would recalibrate the whole system. Our calibration may be off, so we'd recalibrate it and run it again. If that fails as well, then we can say, well, there's something more serious going on. The calibration hasn't fixed it. It's not the calibration that's wrong. It's not a one-off reading. That standard is too low or too high, and so we probably have to re-prepare the standard and the samples that go along with it. I have done an actual webinar a while ago. That was a QA/QC webinar that discusses in quite a lot of detail the different QC standard types, what they're formed for, and where we derive low and high warning and failure limits. So feel free to send me back an email when I send out the one later today, and I can send you a link to this webinar as well if you want more information. Okay, so that's basically setting up a basic method as we described, and now I'll quickly go through how we would actually create a sample list and some actual samples for analysis if we're happy with that method. So we have an option here which is our auto sampler, if we have one. So we can actually set up our auto sampler setup for this particular lab book. So we have a wash time, which is obviously the amount of time the probe stays in the rinse between samples, and our uptake time, which is the amount of time it takes that we delay, basically waiting for the sample to get from the sample to the plasma and stable, ready for analysis. So we can change these. The default is 30. It can be altered in the configuration tool. So we might decide 20 seconds is sufficient, particularly if we've adjusted the pump speed as we did to make it flush faster. Then you'll probably find 20 seconds is plenty of time. We can change the different racks, so we can actually create different rack profiles for each independent lab book. The position on test solutions, where they are, that's actually linked back to the Get Ready feature. As I said, we can do some tests using the standards that are provided, the blank and the multi-element standard, and that's where we can set the positions for those. And we can actually alter our rinse setting. So obviously most people will use the rinse feature on the auto sampler, but some prefer to create their own rinse position. So we could say the rinse is in standard position number 1, and you can see, because there's 2 things in standard position number 1, then it's obviously come back with an error. Change that to 2. So the rinse would actually be at a pot in standard position number 2 there, if you wish to do that. So once you've set up your auto sampler, we can move to the sample list. So this is obviously basically we just set a list of all the samples in the order with the relevant information for how we're going to analyse them. So to add more, we can have add, a little drop down for adding a number of rows. I'll say 5 for the moment. And we can, the label obviously is what we call the sample. So this could be sample blank. 2 and 3. And then we might use a QC sample and sample. And we can basically, for example, move our way along the line to set up the settings we require. So our number of repeats, we could vary that for different types of samples if we wish. If we wish to use the full frame, that was briefly talked over before, then we'd add a tick here. We can add some additional comments per sample. The evaluate, we can tick it off so that we don't actually analyse that sample without removing it. And then we have the sample type. So if we have our drop-down menu, then you can see a whole list of different sample types. So our blank sample would be a blank. Calibration standards called standards. Our QC would be a QC. Now a sample would be an unknown. So the next bit is we can say it says standard. So as we can see, because we've created a calibration standard, it's come up with a warning saying we need to have a standard here. So how do we decide what standard it is? So as you can see, as I drop it down, it's all got all of the standards that I created before. So as I say, there's three ways we can do this. So if we set them all as this calibration standard, which is our 10 ppm stop solution, if you recall, I could put some dilution factors in, and it will set the calibration from those dilution factors. Now remember, this isn't automatic dilution. That feature isn't currently available with the ICP OES. So you have to manually dilute the stock solution, and then it can calculate the concentrations of it from these. So in this particular case, it's a 10 ppm standard stock solution. So calibration 3 would be 10 ppm. Calibration standard 2 would be 1 ppm, that's times 10 dilution, and calibration stock 1 would be 0.1 ppm, so about 100 times dilution. Question asking, yeah. So no, this isn't an automatic. You have to do this manually for the moment. It will be available in the future, but currently no. So we could do it that way with a single stock solution and set the dilution limits, or as we did before, we could just create 3 different standards with the correct concentrations and set all their dilution factors as 1. Now I've set it 3, 2, 1. As we said before, it's gone backwards, so that would be 0.1, 1, and 10 ppm. Okay, so we have some other things that we've seen pop up for our QC. For example, we have what we call the QC action. Again, there's a drop down, which is a list of all of the quality control samples we have in the quality control feature. All of these different ones with the suffix here. So if we choose one, for example, it might be initial calibration verification. And the QC restart is basically asking us if we have to rerun the QC, where do we, or on it passes, where do we start our analysis from again? So our option after previous QC is go back to the last one that passed and run the samples again up till the QC. Alternatively, we can just say move on. If it's passed, move on to the next sample. If it failed and then passed, move on to the next sample. So typically most people would actually use this because their accreditation will require that you run all the associated samples again. Now because we've set our QC as an ICV here, it needs a standard. So it's an initial calibration verification, so we need to tell it what concentration this sample is. So again, we have our drop-down list, and it could be our QC standard, which was 5 ppm. I'll quickly just demonstrate if we were to set it as a blank. As you can see again, because we have a standard, it's saying there shouldn't be one. So this is an initial calibration blank, so there should be no concentration value. I'll just change it back. So we have some other things. A special blank is essentially blank subtraction. So we could, for example, if I was to create another sample here, just move it up, we might call that sample blank. Create that as an initial, so I'll open that as a QC, an initial calibration blank. Again, we'll go for the after previous QC. And we might just say that's our blank sample. We want to subtract that from all of our actual samples. So in this case, we'd for our special blank for our sample, we would create the sample blank. And you could assign it to multiple samples. So it will automatically subtract sample blank result from the sample. And the final part is where are the samples positioned. So we might have these in standard position number 1 to 6. So we can actually select a whole series, and we have fill down, fill up, and increment fill. So if we use the increment fill, it will go on to position 1 to 6. And our sample might be in position 1, so rack number 1, position number 1. So if we move back to here, you can see rack 1, position number 1 is here, and the standard 1, 2, 3, 4, 5, 6 are here. So that would basically create a very basic sample list that we could analyse, and that would produce a calibration, run these 2 or 3 samples, and assign the appropriate QC recoveries as required. Okay, I'm going to stop again and just check if there are any more questions. So we've got one, what does that mean, good calibration will be? Sorry, I don't understand that question. It says, that mean good calibration will be? I don't understand what you're asking in that one, so if you could perhaps rephrase it. Did not get the sample blank point. Okay, I'll try and do that again. So, if you're doing analysis, particularly of any samples that have been extracted or gone through any preparation procedure, you need to check that you're not providing any contamination into your samples from your whole preparation procedure, be it a solid extraction or simply dilutions or carrying the sample. So what you would do is perform what we call a sample blank. So you, for example, if it's a solid digestion, you would put a blank tube with those sampling through the whole digestion procedure, and the acids cook at the right time, make up to the final volume, for example. We would then analyse this as what we call a sample blank, and take the concentration of this and for all the elements, and we can automatically subtract those results from our samples. So for example, if our sample container is adding 10 ppm of aluminium into all of our samples, this will show up in the sample blank as 10 ppm of aluminium, so we can remove it from the samples ourselves. So we would set what we call the special blank for each sample as the appropriate sample blank for the samples you've prepared or created. I hope that's a bit clearer. If not, I'm sure we'll get another question. I do apologise for that voice, as I said before, I do have a cold, so hopefully you can still understand me. Okay, just check no more questions. No. Okay, so I'm going to basically move back now a little bit and look at some of the more advanced features that we can set up in our LabBooks. So there are 2 that we can do very easily. So the first one is what we call the intelligent uptake and rinse feature here. And this is basically a system that we can use to tell the instrument to check when our sample is in the plasma and stable, rather than setting a manual uptake time. And also we can use it, and this is probably used more often for what we call the intelligent rinse. So to make sure that the sample will measure the rinse solution to make sure our sample is clean out between each sample. So the uptake is are used occasionally. It's actually more efficient if you're using internal standard, because we've got something that we know we can measure quite easily. And the rinse would be used a lot, in particular for people that have very varying samples, or potentially very dirty samples, so environmental in particular. Like I say, you can make sure that you apply the correct rinse time for each sample without having to default to a very long rinse time or running the risk of carryover from one sample to the next. Okay, so basically what we have is, on the first bit, we can have the symbol, so it might be iron we're analysing. We can then choose which wavelength that we want it to analyse with. That would be this one, and as you can see, it creates a new line here. So this line is just for setting them up. So once we've created a line, it will come down here. we can decide whether we want to look at the uptake. What's the signal? So once it gets over 1,000 counts per second in this particular case, with a 2% stability on its RSD. So in this particular instance, when we've got these settings, we can change them as we like. What will happen is it will do the uptake delay for 30 seconds here. Just continue. Once 30 seconds is finished, it will start analysing the sample that's in the spray chamber. Once the signal gets over 1,000 counts per second with this 2% RSD, analysis will occur. If it gets to the maximum delay, which is 300 seconds, so once it's been going for a total of 300 seconds, and it still hasn't met the criteria, then it will count as a failure. And we can decide with this option what to do on the failure. So we can ignore it and just continue as we like. We can skip this particular sample. We can abort the lab book or the queue of lab books. So it's quite powerful. You can perhaps, like I say, if you've got an internal standard, then it's very good because you know what signal level you should be receiving. And it would be another additional way of making sure that samples getting in, for example, your tube hasn't split, or the auto sampler has failed, or something along those lines. The other part, and like I say, this is probably used for much more people, is the intelligent rinse. So it's a similar operation. What happens is once the sample is complete, it will run for the minimum delay time, so it will automatically rinse for 30 seconds here. Once those 30 seconds are complete, it will start analysing the rinse solution for the line or elements that we're interested in, that we've selected, until they get below the signal level. So again, here 1,000 counts per second. We can set it for whatever we like. Once it's decided that iron, the wavelength, this wavelength, is below 1,000, it will then continue on to the next sample. As before, if it continued analysing for the maximum delay, so again 300 seconds in total, and hasn't got below this level, then it counts again as a failure, and we've got the same option, so we can decide to skip the sample or abort the lab book, for example. And typically I'd just set a very long rinse time and use this on actually ignore and continue. The only thing we do need to be aware of as well is that we can only do this on one mode, the radial axial mode. As we said before, there are actually kind of four, and it will have to measure all four. So because it's constantly measuring the rinse solution, it has to pick either axial or radial mode to look at. So you have to be aware of that when setting your standards, sorry, your signal levels. So that's how we would set up the intelligent rinse. Once that's set up, then it just runs in the background. And it can be a useful tool, like I say, particularly the rinse, particularly for varying samples. So just before we move on, is there any questions on that? Okay. So another feature we can use, and there are two on here on the quantification that we'll look at. The first one is internal standard. So for those that are unfamiliar with the concept of an internal standard, essentially what we do is take an element that we know is in our samples, it's quite important, and introduce it at a known concentration, or a stable concentration, the same concentration in all of our samples. So that's all of our unknowns, QCs, calibration standards and blanks. Absolutely every type of sample should contain the same concentration of this element. Essentially what this allows us to do is we can measure on our first standard the signal received for this element, and then as it varies from sample to sample, then we can use that to adjust for the varying plasma conditions. So there's a few different things it compensates for. Sorry. So if our samples become very dirty or a very high matrix, then they do what we call plasma suppression. So they actually absorb much more of the energy from the plasma, and so the emissions are reduced for each element. And so this will actually also happen for our internal standard, and because we know that it should be a set signal, we can actually use how much it's varied by to compensate for this suppression. The other one is drift. As our sample introduction system changes, it gets slowly dirty or changes its characteristics over time, the signal will drift, typically sort of downwards, and slowly get a lower signal over time until you clean your sample introduction kit. And again, the internal standard can compensate for this as well, so you get much better stability. So you could run it perhaps over 24 hours instead of over 8 hours without having to do any cleaning or recalibration. So if we want to set an internal standard, we first of all need to select what this element is. So to say, it should be something that we know isn't in your samples. So a common one is yttrium, because it's very rare, or also germanium is quite common as well. And sometimes when doing the analysis of oils, cobalt is a common one, because it's rare in oils. So if we're going to use yttrium, then we need to select some wavelengths to use for yttrium. So what we need to actually do is take a wavelength. We actually require to make sure we match the internal standard correctly to the correct viewing mode. So as we said before, we view the ultraviolet and the visible wavelength separately, and so we would need an internal standard line in the ultraviolet and one in the visible to get best results. So you can see a UV one here and a visible one here. Now, a very easy way to tell the difference between the two is the number in brackets that you can see is what we call the order. So it's the position on the oscillogram that lands on the detector of that particular wavelength. So for visible lines, they are either 100 and something or in the 2 digits. And UV lines, basically 400 is added to the order list to differentiate onto a separate order. So I think that's 400, 500 will be a UV line. It's a little bit confusing. It's only a rough guide, and it does state later on which is which. You'll quickly pick them up. So once we've selected our two lines, if you're interested, if we go to acquisition mode, we can see the two, one high and one low. So we can make sure we've got that correct. We can also see we need to decide whether they're actual or radial. So as we mentioned before, they've got actually the 4 viewing modes. So there's actual high, actual low, radial high and radial low. And ideally for our internal standard, we should match the internal standard line to the analytical lines, so that we get we're actually measuring the internal standard at the same time that we're measuring our sample. So what we've actually got is a high radial line for magnesium and a high actual line for magnesium, and then we have a low radial line for aluminium and a high actual line for aluminium as well. So that's 3. So we've got two high actual, high radial and a low radial. So what we need to do is actually also on top of this produce a high actual line. So if we right click, we actually have an option called duplicate analyte actual. So we've created a duplicate of the same line, one radial, one actual, so we can appropriately match them as required. So that's all 3. Again, remember, if you need all 4, then of course create another low line as well. Okay, so once we've got our wavelengths set up and told them how we're going to measure them, we need to set up our internal standard. So on that page quantification, which I say is actually what do we do with the data that comes out of the detector, we can set our internal standards. So as we can see, we've got our yttrium lines here, so we're going to use them as an internal standard. So for each of those, we select use as an internal standard. And then we need to assign the appropriate internal standard to the appropriate analytical line. So on our aluminium 167, we're going to use the yttrium radial view, that's the ultraviolet one. For our magnesium, we need to, this is a visual line, so we're going to use a visible radial wavelength. And for the other two, we've only got one selection because we've only got one actual. So it separates the actual and won't let you apply actual wavelength views to radial views and vice versa. And that will essentially set up our internal standard with them viewing the correct lines for the correct wavelengths. So I'll quickly just stop. If there's any questions on setting that up, like I say, my other lab book, we can have a look. We've got some actual results that we can view. It's going to take a little bit longer than I was hoping for, so I shall move along a bit quicker as possible. So the other, a final part I'll show you here is what we call line switching. So there's two tables here which allow us to set up our line switching. The standard range actually sets where we want to calibrate this wavelength between. So our aluminium 167, which is our sensitive line, we might set between 0 and 1 ppm. And for the other line, we might do between 1 and 10. So basically what will happen now is the aluminium, as we know, we have a 0.1, a 1 and a 10 ppm calibration standard. So the aluminium will analyse all the standards up to 1 ppm, between 0 and 1 ppm. So our blank, our 0.1 ppm standard and our 1 ppm standard. The next aluminium line will analyse all of the standards between 1 and 10. So it will do our blank, it will do the 1 ppm, and it will do the 10 ppm. And we'll only, so it makes sure we calibrate to the correct range. So again, we can do the same for magnesium. Whoops. 10. And the other part is the switching point. So once we've set up our line switching, in a second, this is basically where does it switch. So when we set up an aluminium trace, basically what they're called, it will calibrate between 0 and 1 for this wavelength. If it measures a sample and the sample is over 1 ppm, it will switch to the next line, which is this one, which is calibrated between 1 and 10. In this case, if it goes over 10 ppm, then no result is given, although we can remove this so that anything over 10 is also analysed. So there's one more step. So once we've set our kind of limits, we can choose the aluminium, one of the aluminium lines. We right-click. There's an option here called Add Customized Multi-Calibration Trace, which is a big mouthful, I'm aware. If we add that on, then we get what we call the aluminium multi-calibration trace. So it's using the two wavelengths, the aluminium 167, the aluminium 309, and we'll use this data and create a line called just aluminium multi-calibration, or we can change it to just aluminium. And so we'll select the best wavelength to give the correct result. And we could do the same for our magnesium as well. So that allows it to choose which wavelength for which sample, depending on the range. Now the other option that we have for the traces, and I'll just very briefly talk about this, is we can use it to, for example, measure oxides. So if we're measuring calcium oxide, we could set a calcium wavelength and apply a formula in there so that it corrects for the oxide levels based on the the different molecular and atomic weights. Again, if you are interested in this, it's fairly niche, then there's a video available on the YouTube explaining how to do it. Okay, so running a bit later than I was hoping for, so I'm going to quickly move on unless there are any more questions. Okay. So what we have is, hopefully you've got the lab book that I sent, or Julian will have sent on my behalf, with the copy of Qtegra, and it's a lab book called Demonstration. So if we have a lab book we want to open, we can go back to the LabBooks page. There's one called Open, and we can find the lab book that we want. That would be Demonstration. And this is one I've created earlier, which has several features in there with some actual results, and I've done some analysis. So as we can see, we've got a large selection of elements with 2 wavelengths each. And they all, I've got 2 wavelengths, so a higher and a lower wavelength for the line switching. I haven't activated the intelligent uptake and rinse. And I've set an internal standard and a line switching feature for each of the elements. Okay, so once we've got some data, then it opens up this extra one called evaluation results. And that includes our concentrations, which you can see here. And in this particular instance, I'll make sure why that's there, shouldn't be. It shows us the multi-calibration trace that I've created for each of the elements. So aluminium, arsenic, calcium, cadmium, cobalt, chromium, iron, magnesium and selenium. And it obviously just gives us a block of data with the concentration measured for each of those samples for each of the elements. If we wish to find some more information, for example our calibration, we can what we call drill down into the next set of data, and it will, for each of these, give us the measurements for the calibration standards. Again, if we open them up, we get some more on the repeats, because I've set them multi-trace. It's a bit interesting. So if we want to come back to our original wavelengths or move things around, we can right-click. We have the option for columns, and so, for example, we could add 2 iron columns back in. Here they are. Just move this one so we can easily compare them. So as we can see, for this wavelength, we've calibrated it between 1, 10 and 100 ppm. And for this wavelength, we've calibrated it from 0, 0.01, 0.1 and 1. And our iron actually includes all of these, and as we can see, it's selected the correct element for the correct range, the correct wavelength for the correct sample range. So in this case, the low for most of the samples, and for our 2 QC samples at 2.5, and it's chosen this wavelength here. So we also get the recoveries for the QC values. If we double click on our calibration, for example, we can see the calibration line comes up here. There's a button for maximize. If we want a lot more detail, we can bring it up much bigger. We can see our R-squared value and some other data as well. If we wish to return, there's a restore button. It will make it much smaller. As you can see on the side, there's actually some more information we have on the quality control. We have the RSV verification, which was the stability verification, so it checks the RSD values for pass. This is also where, if we said there's a regression coefficient test to check that this R-squared value here is above a certain limit. If that fails, then that also shows up here as well. So if we just look at one of our elements in particular and open it up, then we can see we get the data for the 3 repeats, our mean RSD data as well. And for the elements with actual calibrations as a specific wavelength, it will show our calibrations. There's a quick overview here as well. So you can quite quickly drill into the extra information that you've got. But we also have a page of intensities. So as we can see, these are the actual signal that the instrument has received for each of the wavelengths. And by double-clicking on one, we can open up the subarray. So that's our subarray feature, what the instrument actually is seeing for each of the pixels across the wavelength. And we can move, if we wish to move positions on here, then we can do. So again, we have to maximize screen so we can make it easier to see what's happening. And we have our central pixels, which is the measuring the peak. And we can add more on by clicking on them on the left and right, as we wish, or remove them by unclicking. We just change it slightly. And again, with our background, so then it will remove our background points. So we can simply move, select them to choose different background points, to right or left, or of course we can remove them completely. If we've made changes that we wish to keep, we press, well, I'm going to move back, simply press the apply changes, and you'll see that the results automatically alter and are processed. And this can be done for any of our different elements as well. We also have you can simply move through the analytes quickly with the next analyte, previous analyte button. If we want, we can select several and overlay them all over the top of each other so that we can compare the different subarrays that we have from sample to sample. Right, so there's one other feature then. So we've had a look at the, discuss the line switching, quickly set up the internal standard, and our intelligent rinse and uptake. There's one other feature that we have that we call IECs, and that stands for inter-element correction. So this basically allows us to, if there's an element that's interfering with another wavelength we're interested in, then we can compensate for this if we can't find a better wavelength. So I've set one up in here in particular, so one of the cadmium wavelengths interferes with arsenic, or sorry, arsenic interferes with one of our cadmium wavelengths. So as we can see here, this is actually a 10 ppm arsenic solution, and our cadmium line is clearly got a severe interference that's causing problems that will cause us a false measurement of cadmium when there isn't. So if we move back to the concentrations, find the cadmium, as you see we've got a result. I'll just open up the actual cadmium wavelengths so that we can see them more easily. One. So we can see for this wavelength we've actually got a result of 0.043, even though that we know there's no cadmium in that particular sample. It's only arsenic. So if we want to remove that, we can do what we call this IEC compensation. So if we find the interference here and right-click, there's an option right at the very bottom called inter-element correction. It brings up this window here so that we can set what we need to do. So what we do is we find the wavelength, cadmium 214, right, no, 228, sorry, which is this wavelength. Sorry. So we need to find, sorry, the element that's interfering. So in this case it would be arsenic. So we can select the arsenic here and say it's arsenic that's interfering. We want to measure the arsenic for this on this particular wavelength, 189, and use that to compensate for the cadmium wavelength. So there's a feature here, we can see the little circles going around, which is our auto calculate. So if you press that, it will automatically calculate a formula for the arsenic. If I press 0 and go back, where is our arsenic line? Click OK, swap the line. So what's happened is it looks at the arsenic line we selected, which is this one, and it says when I see 14,312 counts of arsenic on this line, I need to remove 1,593 counts from that cadmium line to set it to 0. For example, if it sees 7,000 counts of arsenic, then it will remove half of that, so about 800, just below 800 counts of cadmium. So it will measure the arsenic and compensate the correct line by the correct amount to compensate for this kind of effect that we can see. See, some are much more subtle than others, so in this case it's obviously very obvious that there's a problem here, but sometimes they only create small sort of bumps in the side of our peak, but they're equally valid at causing false results. We need to be aware of that. Okay, so just got a quick question. How do we find out the interfering elements? Okay, that's quite a question. Okay, so if I just we look at this one and we see this and we don't know that's arsenic, I think is the question. So if we just make this peak a little bit bigger, and basically we can select on the wavelength on the peak here, and we can see what other, we've got this what we call a wavelength finder. We can see what other peaks are around at this particular location. So in this case, we will try and select somewhere near the centre of the peak, best we can, and it will give us a comparative list of all the other wavelengths that are around there. So simply by selecting a location, we can see that in this case it could be scandium or arsenic, because those two wavelengths there are very close for two scandium ones and an arsenic. And to be honest, the only way to tell the difference between the two would be to run a single element solution for those two wavelengths. So in this particular case, you would run a scandium, say for example a scandium 10 ppm and an arsenic 10 ppm. And it may find that they're causing both, that both of those are causing interference. But you could also run your sample for both of those elements, and you will see perhaps there is only arsenic in your sample or scandium in your sample. So it's a little bit of experimentation required to find exactly what it is. But we can use this wavelength finder feature, and it's simply by selecting an area on the peak, on the subarray, and it will tell us what wavelengths are in and around that area. So that's a tool that will narrow down your search to perhaps one or two or maybe three elements, and you'll basically just have to test all three of them really. Now some of you perhaps are familiar with ICP does also have this feature, but it works in a slightly different way. So in Qtegra here we use the counts. So as before, when it sees a certain amount of counts, in this case the 14,000, it knows to remove the 1,593 from cadmium. So it's basically measured entirely on intensities. In ICP, it's on concentrations, so it would be in the same way, but it actually has a measured concentration for arsenic, and then says, okay, for example, when I see 10 ppm of arsenic, that would mean that I need to remove 0.4 ppm of cadmium, for example. So the advantage of the Qtegra one is that we don't have to actually calibrate for the element that we're interested in. We can just add our interferences on as a separate, an extra peak without having to calibrate for. Okay, is there any more questions on the bits that we've covered? Okay, that's good. So we've got about half an hour left. I do want to leave an area at the end for questions. I was hoping for half an hour, but because we've hopefully done most of them on the fly, we should be okay. The other bit I'll point out then with our results is our internal standard. So we get some measurements for our internal standard, and as we can see, they're measured as a recovery. So it takes how many counts is measured for the internal standard on the blank, and simply compares all the other results to that measurement for the blank, and makes a recovery. And so in this particular case here, for example, it's got a recovery of 77.1%, so the internal standard is low. So it assumes that our sample is low by the same amount for those viewed in the visible actual range in this particular instance. And so we'll just assume that all of the samples are 77.1% of what they should be, or what they are, and we'll mathematically compensate by just multiplying them up by that factor. So that's applied automatically. And as you'll find, if you do some testing or some analysis, that it's extremely accurate, very, very good. And I'd suggest using an internal standard for all analysis, but particularly anything with difficult or varying samples. So you will find it useful. Okay, so just going to double check that that's everything on the list. I've made a printout and I forgot to put it upstairs. If anyone's got any questions of anything that we've covered so far. Okay. So I'm going to... Okay, why are some cells marked red, blue, yellow under intensities and concentrations? That's quite a good question. So if we go to concentrations, it's basically a very simple system. So the different types of samples are marked with different colours. So our blank sample, calibration blank, is blue. Our calibration standards are yellow. Calibration block, the standards is yellow. And in QC samples we run a red. And the unknown ones are sort of this grey-white colour that looks like nothing. So it's simply so that you can very easily see which ones are QC samples. They stick out much quicker. Now for our little analysis that we've got here, then that's not really a huge problem, because we've only got a few samples. If you're running 100 samples and there are QCs every 10, then suddenly it becomes more difficult to see what's what. And so it's designed to make them stick out. If we move to our sample list, hopefully you can see we have the same colour coordination in the actual list of samples that we've analysed. So we've got the blue for blanks, yellow for calibration standards, red for QCs, and blank, sort of white, grey colour for our unknown samples. Hopefully that answers that question. The other bit we'll see as well, if we've got, for example, a QC that failed, then it will come up as a red result as some sort of failure for some reason, because this one's fallen outside its pass and fail parameters. But in this case, we're not interested because it's outside the QC as well, so we've used the iron and it's selected the right way for us anyway. And a similar thing we can see with our internal standards. These particular samples have come as warning limits, and so they've gone yellow, or an orangey yellow colour for the warning limits. Another thing we can show you, I can show you as well, if you get some that come up as blue, as your results that are blue, then that means simply that the chip has been saturated on that particular wavelength for those particular samples. Which is why for magnesium I've used this wavelength for the low section and this wavelength for the high section. It allows me to get very good detection limits on the sensitive wavelength and the much higher range on the less sensitive wavelength. Okay, I take it that's all of the questions that we have for the moment. Okay. So there's another feature that I briefly talked on before called templates. So as I said, we can create a template for our routine analysis and use that to create LabBooks every day that are in the same format. So again, we can go to our template tab here, and it's similar to the LabBook one that we saw before. So we can create a template, call it demonstration 1. Again, find a position for it, and we can do the 3 things. We can create a blank one, which is like similar to the LabBook we set up before. We can create a template from a template we already have, or we can create a template from a LabBook that we have. So if we run our LabBook demonstration as our method development, and then we want to create a LabBook because we're going to run this now we're happy with the method, and we're going to run it every day for our routine analysis. So I shall do it in this particular case. So if we press create template from this LabBook, we can see that all of the system settings are carried over. So our wavelengths that we've selected, the measure modes, the acquisition parameters, any interrelevant corrections we may have set up, the standards we've set up, all the quantification. So all the method settings are transferred over straight away. Our auto sampler is as well. Now the only difference is instead of a sample list, we have this what we call sample definition. So it doesn't do, you don't use your template to actually do analysis itself. You use it to set up a set of definitions so that we can create our LabBook the same each day. And as you can see, what we've got is 3 called the initial actions, the continuing actions, and the end actions. And we can add sets of samples to each of these. So if we go to add initial actions, okay, so we can add a few, maybe 4. We can set these as our blank, calibration, then set number of repeats. Do we want a full frame? What type of samples they are? So in the same way that we set up our sample list before. I've set this particular LabBook up with a series of dilutions. Remember, these are manual dilutions that I've performed, and just simply told it a single standard. So for some people that would be useful. If you've got, like I say, a single stop solution you create, dilute it down to make your calibration standards. And for some people then creating them independently, as we discussed earlier, is beneficial. So we do actually have the amount, the final quantity, which again is a sample list. So if we want to do dilutions, for example, we put 1 gram of solid sample and made it to 100 milliliters. We could add that in instead, that dilution factor, and it will apply the correction factor or dilution factor as needed. Once again, we put positions for these, 1 to 4. So it's basically saying at the beginning of our LabBook in our sample list, please create a calibration block with these particular calibration standards. We could add a QC sample as well at the beginning to say run a QC sample to make sure everything's okay. Again, we want it to be an initial calibration. Let's go to the previous QC and to run a QC standard. This might be position number 5. So the initial actions will always add them to the beginning of our sample list. The next one is continuing actions. So it's basically what happens in the middle of our analysis. Okay. So what we have here, this one that's locked, is our sample. So if we are adding samples in, we might call that sample. Oops, sample. And then we're going to run a QC sample as well. And we decide that every 10 unknown samples that we run, we want to add a QC sample automatically. So in this case, we'd add it as the interval. Let's say it's QC. Set up our standards as before. So it could be a continuing calibration verification. That's a QC as well. And this one might be standard position number 6. And then finally at the end, we have our end actions which is quite straightforward, and it's exactly what it says on tin. It's what we want to do when all of the samples have been analysed. What do we add to the very end? So again, this could be QC with the same continuing calibration verification. And it's our QC. So this could be standard position number 6. So if I save this now as our template, so we can save the template, we could give it a comment if we wanted to. And that's saved. So then when we come to do our analysis, for example, the next day, and say we want to create a lab book using this template, we go back to the LabBooks template. We'll give a name for our lab book, so that could be demonstration 2, the date. We go create a new lab book from an existing template, which is the template we've already created. So we select the template, which is number 1. How many samples do we want? Well, it might be 32. And like I say, we can use it to create an import from the CSV, which will just take the sample, a list of samples that you've created in your lens, and just simply populate the template that we've set up with these samples. If we go create a new lab book, demonstration 2, as you can see, what's happened is it's set the initial block that we set up, the calibrations for the QC, done 10 samples, another QC, 10 samples, another QC, etc., etc. And then it's got to the end and it's added the end actions, the final QC at the end. We can change the names, sample 1, 2, or whichever we want to call them, and assign their rack positions as well. So it's a basic way of, you could then create a lab book from this template each day, and it will lock in all of the calibration and QC requirements that you have. So are there any questions on templates that we've got? Any? Okay. Well, I shall leave that for the moment then. Like I say, a lot of these features already have videos on YouTube that you can go back and have a look. And I will send out the video for this so that you can view it again if you require. Okay, so something else that we have, so I'll quickly go back to this, is if you're using a LIMS system, you might want to automatically export your results into the LIMS system. So we use a CSV export file. So when we're creating a new lab book, there's an option for automatic export. So we can select the CSV export. We decide we want to automatically export a CSV file or a spreadsheet, an Excel spreadsheet file, and you can do both. Let's just set one for the moment. And we can decide quite easily what we want to go into this export file. So we can decide we want the concentrations, quality control data, pass and fail, okay, and limits and detection, for example. We can actually open these up and put specific things, so we might only want the average or the standard deviation as well. So we can very easily select what we call these schemes, what system we want. And if we've created one that we're going to use over and over again, we could press save, give it a name, of course a description, press save. So this means that we've got the scheme here, so when we open a new lab book, and we decide to set up an export, so here for example, we can simply go and select that each time without having to set the conditions that we wanted. So the other features we've got on the side then for actually exporting it are We can decide how we want to separate it. Is it tab, semicolon, custom feature? Do we want to use a point or a comma, depending on where you are in the world, as your decimal point? And how to export them. So we can export the sample lines as rows, export the groups as blocks, export the whole lab book, or just export specific samples. So that's our kind of option. So is it saying, as a sample comes up, export a separate file for each sample, the LIMS will go and grab that file each time, or do we want to wait till the lab book's complete and then export the whole thing as a single file? And basically what this will do is every time either a sample or lab book is created, it will export this CSV file to a given location. Delete schemes as well, save it. The other section we have is what we call a report export. So again, in a similar fashion, we can have it automatically create a report once the lab book is finished. So we could create it per sample or per lab book, as we discussed before. Choose the type of sample report that we have. Choose what to do with it. Do we save it as a PDF? Do we save it as an RTF? Do we send it to the printer? Choose what the target file name is if you're going to save it as a PDF. Or we can choose, which printer do we want if we're going to send it to the printer. So again, you can get it to quite easily automatically create reports and print them off as your analysis is complete. It's a quick and easy way of doing it automatically. So what we can do, if we've got actual results, if we've already done some analysis and got results, we can, manually pull up some results as well, some reports. We simply select on the option here, reports. We have our option of default reports that come with the system, and we can simply select one, and it will load the data from our lab book into said report. Depending on which one we want. So the majority of them there are covered. So what most people will want should be covered quite easily in this set of reports here. It is possible to create your own custom reports and decide what you want to go in it. Two easy ways we can go about doing this is there's a feature called Edit Report here, so we can adjust once it's already set up. Or if we do go to Query here, go to Reports, we can create a new one as well with the new report. So we can create a manual one. I won't go into that because I could spend the next hour talking about doing it, so I shall leave it for the moment. I'm not sure whether Julian will talk about it in more detail, but he has produced some videos on how to do this, and I will make sure they're uploaded to the YouTube site that I sent out. So we're getting quite close to the end, so I'm going to stop to see if there are any more questions. Okay. We've managed to cover everything. There is a feature here, like we say, the query, which allows us to search for certain information that we want. So we can simply select the information we want, and the concentration average. We want to make sure we've got the results. We can simply refresh, and it will give us a page that's just the concentration results that will come up in such a simple way, so that we can select them and just copy and paste them if we want to do it that way around. Or if we have our sample list, we can click on any samples. Let's export to Excel, or select several as well. And there's an export. An export to Excel feature here. Or again, we can just copy and paste. So I'll just quickly do the export to Excel feature. So if we press this, all the rubbish on my desktop. And I'm going to call this demonstration 1. We've got one. We can choose do we want it as an Excel file. Yes. So we press save. Change the 1 second, just find it. Where's it gone? Like get on to share my desktop. Hopefully we can find Excel. There we go. So we can open up our Excel sheet that we've exported, and as you can see we get almost exactly the same thing that we've got, that we've copied from our oops, this. Why is that not? What have I done? Exported the wrong thing. So that we can export our sample list, sorry, so I've gone to the sample list, we could export our sample list as I've done here, which gives us the list of things we've run. Of course we can go to our concentrations, and export to Excel. Again, just call that demonstration. Here. So we can see we get all of the kind of data as a subset like we have in the concentration page, and we can open up and get any of the information we need again. Or alternatively, we can select several samples, simply copy and paste them into our Excel data to get results quite easily that way. Okay, question here. Okay, so I've got one more question. Can we print from the query report page? Okay, so we've brought up this page here. Unfortunately, there's not actually a print feature as such. So, as I say, the best way is to export it into an Excel and print it from there. Unfortunately, like I say, this query isn't a printable feature, but we could quite easily create a report which does have the information that we want. So if we can select one, press the display reports here. We can easily just print out using the print button there. Like I say, it's possible to create custom reports, so you can make them show just exactly what you want in the way you want them. But it's something we haven't got time for at the moment. So hopefully Julian will cover through, or there will be. He has made some videos explaining it anyway, so you can have a look at those. That. Because now we just need to start working on the software and see if you have any questions. Okay. So we've got about 5 more minutes. So if anybody has got any more questions or anything else they'd like to ask me, then please feel free. I'll just unmute everyone off the phone. No, apparently I can't. Never mind. So if you have any questions, then please type them in, because the mute seems to have gone wrong. And we can answer them now, or alternatively, like I say, I'll send out an email by the end of the day that has this recording, and also a link to the YouTube channel I've talked about with the videos I've prepared. And please feel free at any time to email me back with any other questions that you do have, and I'm more than happy to help you do what you need to do. So hopefully that's cleared it up for some people, or showed some extra features that we weren't aware of. Hopefully we can help you do the analysis that you need to do. Okay, that's saying somebody hasn't got an email. The list of people that I got that accepted this up till yesterday, I sent through to Julian, who will be doing the ICP one. He should have sent through a link for you to download a copy of Qtegra that you can use to test out, and with some demonstrations in there. If you haven't got one, you can either type it down now or send me back an email when I send one out. Then I can get that sent out as well. Make sure that I've got a list of everybody that's on. Can you use existing calibration, or do you need to create another one at the beginning of each run? That's a bit of an interesting question. So what we can do is, unfortunately for each lab book does have to have a calibration in each lab book, so you can't copy the calibration from one lab book to the next. So in that sense, yes, you need to do a new one for each lab book, but you can at any point add more samples to your lab book for analysis. So as you can see, we've got the demonstration one we were looking at with samples we've done, and we can actually just add some more samples on, call them what we like, and press run again, and it will just run those samples that we've added. So if you do wish to just use the same calibration over a period of different days or over the same day, then that's perhaps the way to do it. Just bear in mind that I think there is a limit to how many samples you can put in a lab book. I think it's 2,000. On my list of things to try and update or change is we could perhaps get more in there, but you will have to be aware that there is a limit in there. Hopefully that's answered your question. Okay, so that's almost the same question. So like I said before, if you want the same method, then if you're going to create new lab books, then you'll need to put a calibration in each lab book. It's just obviously at the beginning. But you can continue to add samples to the same lab book, and it will continue to use the same calibration that's already in that lab book. Hope that's answered it. If not, then please let me know. Okay. So I think that's everything. I was just trying to see if I can make sure I've got everyone's names, but I think that's saved in the software somewhere. So thank you very much for being on the call, and hopefully it's helped out at least a little bit. So I'll send out an email by the end of the day. If you haven't received it for some reason by the end of the day, then please contact one of your local contacts, and they will get in touch with me and make sure that I can send it to you as well. And if you do have any more questions, then please feel free to email me back, and I will help you as best as I can. Thank you.